Today we're talking about a paper that sinters silicon carbide at an extremely low temperature. And it caught my eye because it uses kind of pretty common ingredients that are easy to get and pretty minimal equipment as far as sintering goes. So I tried the protocol and it went great. And I got a result that looked just like the paper. And I thought, perfect. For once, I've got a project and a video that went according to plan. It'll be short and simple and I'll get it out quickly.
Mr. Taps would soon find that the project was neither short nor particularly easy. This would cause him unending distress in the days to come.
But the more I thought about the results, the less confident I became in the described mechanism of action of how this is supposed to be working. And I'm definitely not an expert in this field, so I decided to start running some more tests to prove to myself that it actually was working. I assumed I was just forgetting something or wasn't understanding a principle of it. And the more results I got back, the less and less confident I grew about the paper. So today we're talking about the paper, the protocol, how it works, and then my follow-up test to try to determine what's going on here and present some hypotheses about what's actually happening and whether the paper is correct or not, because I think it actually lies somewhere in the middle. But that's jumping ahead, so let's talk about the paper first and why it's interesting even to begin with. So this paper is interesting because it's sintering silicon carbide at a very low temperature, 600 degrees Celsius or thereabouts. And that is very interesting because silicon carbide is a fascinating kind of super material. It's incredibly hard, almost as hard as diamond. It's chemically inert. It has extreme heat resistance. Up until about 2700 degrees Celsius, not a whole lot happens. It just sits there kind of baking in the heat. And then above 2700 degrees, it just sublimates away. It vaporizes into the air. And so that has a really useful property, especially because it's a semiconducting material, which means that you can make semiconductor devices out of silicon carbide instead of just silicon. So there's a lot of interest in using silicon carbide for high temperature or astronomical electronics. Now, all these wonderful properties also is its big downfall in that silicon carbide is just really hard to work with. It is physically hard, so it's difficult to machine. It's chemically inert, so you can't just dissolve it in some solution and precipitate it back out. And because of its temperature resistance, it's really difficult to sinter silicon carbide grains together. It requires excess of 2000 degrees Celsius to do kind of direct sintering, or you can do other schemes like reaction bonding where you melt liquid silicon to infiltrate in between the silicon carbide grains, also at really elevated temperatures. So all the ways to actually process this material are extreme, which limits its use just because it's so difficult to make parts out of it. So when you see a paper that says silicon carbide sintering at 600 degrees Celsius, it catches your attention because that is shockingly low for silicon carbide. It's practically in the refrigerator. The paper is super straightforward. You take 3 ingredients, silicon carbide, cornstarch, and borax, mix them all up, throw it in the furnace, and you get your silicon carbide part out the other end. The silicon carbide that I'm using is 500 grit sandblasting media. It looks like these sharp little flat platelets that are 15 to 30 microns wide. Cornstarch is cornstarch. It's the stuff you buy at the grocery store. And borax is like the detergent borax that you also can buy at the grocery store. The silicon carbide's purpose, I think, is pretty clear. So we'll focus on the other 2 ingredients. The cornstarch is used as a binder to help hold the green part together before you put it in the kiln. In this paper, they're using anywhere from 30 to 50% starch, which is a lot of binder compared to most applications where you only use a couple percent. And the reason for that is they wanted the porous nature of having all this binder get burnt out. So if you wanted a denser part, you would just use a lot less binder. And that leaves us with the final ingredient, borax. Borax is used as a detergent, which is why it's sold, in your grocery store, but it's also a fluxing agent for melting glass. So if you want borosilicate glass, for example, you'll add boron and a small amount of sodium, both of which are available in borax, and that lowers the melting point of pure silica to the point that it's a lot more workable, say 1000 degrees Celsius. And that's the key insight to this paper, even though it feels unrelated, right? What's glass have to do with sintering silicon carbide? It's relevant because silicon carbide naturally has a very thin layer of oxide on top of the surface. And that oxide layer is silicon dioxide, or silica. As you heat the temperature, that oxide layer also grows, which means you can get a reasonably thick layer of silica just sitting kind of on the surface of every grain. So the insight here is if you put a fluxing agent for silicate-based glasses in with the silicon carbide, you can actually melt a glass in between the grains of the silicon carbide and sinter those grains together. A lot of the paper was about the porosity of these parts, and so they have a lot of different combinations of silicon carbide, starch, and borax to see how that affects the pores. I tried a few of them and they seemed to work, so I mostly focused on one sample just to simplify my life and really dial in that procedure for one of the recipes. The protocol itself is super straightforward. You take the ingredients in the correct proportions, mix them up well. The paper used a ball grinder. I mostly just did it by hand or threw it in a rock tumbler. Next, you make a slurry by adding 50% solids to 50% water and pouring it into your mold. I tried a variety of different molds, metal, glass, molding it with silicone. Ultimately, I settled on silicone because it let me make more interesting molds more easily, and it was relatively non-stick. The paper calls for aging the slurry in a drying oven for an hour, and the purpose of this is that the elevated temperature will make the cornstarch gel up. Just the same reason you use cornstarch in cooking to kind of solidify dishes. The same thing happens here. So it makes the part become more solid, and in theory you can then demold that and put it into the furnace and you kind of have the full complete part. I didn't find that to work at all. What ends up happening is the top surface will form kind of a dehydrated skin while the lower surface stays pretty wet. And even if it gels, it stays really sticky for pretty much every surface that I tried, including silicone. I was using a hot plate at first, but eventually I switched to a food dehydrator, which did a better job. And ultimately I found it was just easier to fully dehydrate the sample for 24 to 48 hours. And that made it a lot easier to demold because you had a completely dry part. It has pretty considerable shrinkage too, so it pulls away from the walls of the mold and you can pop the part out a lot easier. There are a lot of different binders you can use, so I tried PVA just to see if that would be a little easier. But I actually didn't realize that when you mix PVA with borax, you make silly putty or oobleck or whatever you want to call it. It's kind of a non-Newtonian fluid that instantly gels up when you mix the ingredients together. I also tried silicone, PDMS, as well as urethane, and both of them sort of work for different degrees, and it's something I would like to look into in the future, but I just went back to the paper and used starch and just accepted the long drying time. From there, it's into the furnace. The paper used a ridiculously slow heating rate, 1 degree Celsius per minute. So to get up to 600 degrees Celsius, it's like 10 hours. The reason I think they did this was to slowly dehydrate the samples, because if you put the wet sample in and crank the temperature right away, all of that water is just going to boil out and you'll foam your part up and make a big mess, and it won't keep its shape anymore. Since my parts were mostly already dry from being in the dehydrator for 48 hours, I turned the heat up to about 200 degrees, let it sit there for a while, make sure all the moisture really was gone, and then crank it up to 500 or so degrees to burn out all of the starch. And that takes an hour or two. You can pretty much tell when it's done because it stops smelling like burnt starch and you don't see smoke anymore. And from there you can turn up to the final temperature, 600 degrees, and let it soak there for an hour as the paper calls for, and let it cool back down. And hey, it worked. You get samples out the other end that look and feel like a piece of ceramic. They're notably lighter than when they went in, and they have kind of a ceramic-y sound when you scrape them against each other. I took some of the samples before they were fired and after they're fired and put them in the scanning electron microscope just to see what was going on and if it matched the figures in the paper. Here's a photo of a piece before I fired it. You can see that there's little silicon carbide grains scattered around. They seem to have some type of kind of liquidy network holding them together. That's most likely the borax, which is soluble in water, so it gets kind of spread evenly everywhere. And then long filaments kind of stretching between places, maybe ending in kind of nodules. And that's the starch that has been polymerized out and then dried in place, and it forms kind of this filamenty, muscly fiber network. In contrast, when you look at a sample that's been fired at 600 degrees, you see all the filamenty starch stuff completely go away. It's gone no matter where you look, and you're just left with the silicon carbide grains and that kind of liquid looking surface in between all the grains holding everything together. Different areas have more or less of this nature. Some areas look drier, so to speak, than others, and I'm not sure why. I kind of chalk that up to not a fully homogeneous mixture. I was just mixing this by hand. But if we generally compare it to the figures in the paper, we can see that they look reasonably the same. They have the same kind of morphology in both. The paper didn't do this, but I was really curious about the mechanical properties, and I felt like that would be a really good test to see if this actually did anything. Like, did the material become stronger or more ceramic-like than before it was fired? So I set up a 3-point bending test and ran an unfired sample first, and you can see that it doesn't really behave like a ceramic at all. The crack starts to slowly propagate its way up. It's not a brittle fracture at all. It's kind of just peeling apart, which absolutely makes sense. It's essentially silicon carbide held together by dried starch glue. But when we look at the fired piece, you can see that there's essentially no deformation while it's being compressed until it suddenly fractures in a very quick, brittle fracture event. And this is classic hallmark ceramic, where once a crack initiates, it propagates super rapidly, and then the whole thing is blown apart. We can calculate the modulus of rupture, and the fired example is a lot higher than the non-fired example. I'm not a civil or mechanical engineer, so I don't really know if these numbers are good or bad for this type of material, but one is bigger than the other, which makes me feel like it worked. Cool, okay, video over, right? Hit that publish button, go on to the next thing. I wanted to, I really did, believe me. I wanted this to be a quick and easy video. But something was just nagging me while I was looking at the images and collecting some more scanning electron micrographs. And it was the kind of like liquidy looking interface between the silicon carbide grains. Because of the explanation that there's a thin oxide layer on all these grains and they get joined together to form little glassy bridges. And that's helped by the borax fluxing agent. But it looked like an awful lot of glass in between these grains. And I started thinking about it more, and the borax doesn't go anywhere, right? It melts at a higher temperature, 750 if I remember correctly, and it's not being leached out in any way. So all of that borax is still sitting here. Is this thing that we're seeing actually just borax holding all the silicon carbide grains together? Like, is this sintering at all, or is it just a filler material, the carbide, with some borax glue around all the edges? So this caused some soul searching and existential angst, and questioning why I do this to myself.
It's been hard in America. It's been tough, feeling sad.
But ultimately, I decided to take the sample from the 3-point compression test and break off a piece, image a known section of it to see kind of what the morphology looked like, and then drop it into some boiling water and then re-image. The idea is that if this is just borax that's holding everything in place, it should be soluble in water and it'll dissolve the piece immediately. So I dropped it in, boiled it for, I don't know, a couple hours, came back, dried it off, and while I was mounting it to the stub for imaging, it collapsed. Not the whole thing, but a pretty sizable amount of it just kind of flaked off into powder, which was not a good sign, in my opinion. That really made me question whether this is anything at all or just borax holding stuff together. So I repeated it with different samples, and I didn't have quite as dramatic of effect as that one. And so the samples held together, and I was able to get matching images before and after boiling, but you can see morphology changes between the two in some places. So in some places, nothing changes. In this image, for example, it looks reasonably the same between the two. But in other locations, you can see a pretty distinct change where the individual grains of silicon carbide become much more pronounced. That kind of liquid network in between has gone away to some degree. This variability was maddening to me because I couldn't get it consistent enough to really definitively say, yes, this is what's going on. So I did repeat this a bunch of different times, and essentially the end of the story is that in some cases, the morphology changes when you boil it, and in some cases it doesn't. And in extreme cases, the part just kind of crumbles back into silicon carbide dust. So that's where we're at. I don't know what's going on, but I have 3 potential options, and I'm curious to see what people think is the most likely. So the option number 1 is that I messed something up, which I'll be the first to admit is entirely possible and is probably the most likely. Whether I did something wrong mixing the ingredients incorrectly, not homogeneous enough, impurities in the materials that I was using, the base materials. The furnace I'm using doesn't have particularly good temperature control, so maybe it was fluctuating too much. Maybe this effect only works at 600 degrees in a very narrow band, but no more or no less. There's a lot of different ways this could have gone wrong that was essentially something about my setup here. So that's option 1. Option 2 is that there is little to no oxidative bonding between the silicon carbide grains. So that proposed mechanism of glass forming in between the individual grains, that's not actually happening, or not enough to really do anything. The paper does do gravimetric thermal analysis of their samples to see when or if the borax crystallizes by itself or in the presence of silicon carbide. And that data is fairly convincing that the borax isn't like crystallizing on its own to make a crystalline network. So it's likely just amorphous borax kind of hanging out there. And when you add water, it washes all away. This is fine. There's nothing wrong with that. Like, there's a lot of composites that are essentially an inert filler surrounded by some type of binder or glue. That is essentially what carbon fiber and fiberglass is, but it's not quite sintering in my opinion. So if option 2 is the case, I don't think this is really sintering at all. I think it's just a composite. Option 3, which I think is my favorite explanation for what's going on here, is that the oxidative bonding is happening between the individual grains, and you also just have a lot of borax hanging out, kind of filling the spaces between, because it's like 30% of the recipe, so you'd expect there to be a lot. However, I think what's happening is that the glass that's forming is a borate glass rather than a borosilicate glass, or more borate than borosilicate. And the reason for that is that the oxide layer that's on top of these grains is very thin, so there's just not a lot of silicon dioxide to work with, but there's a whole bunch of boron and sodium from the borax. So whatever glass ends up forming is going to be really borate heavy and silica light. And borate glasses are water soluble. So that could explain some of the variability that we're seeing. The borax washes away immediately in the hot water, and then the glass bridges that are left, the ones that are really strong and robust because that region happened to sinter well, are more resistant to dissolving, whereas other regions that have very light glass networks dissolve away quickly. And I didn't keep good records of this because I wasn't thinking about it at the time, but anecdotally, the samples that I boiled for a long time fell apart more readily than those that didn't boil for as long. And more anecdotally, I took one of the samples and I fired it at 1,000 degrees Celsius instead of 600 degrees Celsius, and it seems resistant to boiling and falling apart. This is potentially because the oxide layer is much thicker at elevated, longer temperatures in the kiln, and so there's just more silica to work with, and it makes more of a borosilicate glass and less of a borate glass. So that's where we're at. I'm tired of working on this, so I'm just going to leave it with 3 potential hypotheses. I'm curious to know what people think. This is not a field that I'm overly familiar with, so it could be that I'm overlooking something really simple, or maybe I just didn't read the paper quite closely enough and they come out and say in, fancy academic terms that this is a composite of borax and silicon carbide. I don't know. Do want to say thanks to all the folks that support me on Patreon. I really, really appreciate it. It lets me go down these ridiculous rabbit holes of sintering silicon carbide for a month. and I deeply appreciate all the support you've given me, so thank you. If you'd like to support this channel, there's a link somewhere to Patreon. If you're not subscribed already and enjoyed today's video, please consider subscribing. We have a Discord channel. I haven't mentioned it in a while, but the link's down below. Lots of cool folks from academia and industry, students and hobbyists, all talking about different fields. It's actually a really fun server with a lot of interesting and intellectual conversations. So check that out if that's your jam. And otherwise, I think I'll see you next time. Thanks for watching.
Mr. Tapswood soon finds that the project was neither short nor particularly easy. This would cause him unending distress in the days to come. I don't know why I did that. Oh, God.